Okay. All right, so I'm going to start talking about computational interpretation. I think the main thing I want to do, I wrote out some notes. It's probably more than I'll get to today, but I kind of want to go slowly and interact and like ask me questions and stuff like that because it's a good opportunity to do that. So whatever we get through is fine, and if we have to do another one of these, then that's cool. But the main thing I want to do today is kind of convince you why I think there will eventually be a computational interpretation of univalence, because like I know that like I kind of feel that more than other people do, and so I kind of want to give you the sense for why I think that we'll get there eventually. And the technical stuff that I'll talk about is this work with Bob Harper, my advisor, about two-dimensional type theory, which is sort of the simplest possible case of something that's more than regular old extensional type theory kind of things, right? So like two-dimensional type theory, you have just regular groupoids and not higher dimensional groupoids, so the whole game is easier to play. But okay. But before we get there, I want to do something that will be review for some people, but maybe not, maybe a new perspective for other people, which is to talk about, just for like 5 minutes, Genson's natural deduction. Because there's a request from Mike back in one of the first meetings about like people that it would be useful to like say a little bit about how to think like a type theorist. And I think talking about this particular perspective on computation is useful for setting up what I'm going to do later. So like with natural deduction, has anyone not seen natural deduction before? Okay, good. Okay, so just to review, if I want to prove that A and B is true, I'll have what's called an introduction rule with two premises that says that if I can prove that A is true and B is true, then I can prove that A and B is true. Call that conjunction introduction. And then I'll have what are called elimination rules, which says if I can prove that A and B is true, then I can conclude that A is true. And if I can conclude that A and B is true, then I can conclude that B is true. Okay. And the whole point here is that you get computation to arise out of introductions meeting eliminations, right? So there's this perspective on computation that computation comes from proof reduction. So this is computation as proof reduction, where if you have something like, well, I derived that A was true by some derivation d1, and I derived that B was true by some derivation d2, and then I derived that A and B is true there, so that's applying conjunction introduction, and then I immediately apply conjunction elimination to get that A is true. Okay, so that's a proof with a detour in it. Right? I introduce A and B as true and then immediately eliminate it. And the principle is that when you have introduction followed by elimination, then you should be able to justify this by giving a computation step that computes a simpler proof of the thing that you concluded. And in this case, that's just the proof D1 that A is true. Okay? So the key idea is that this notion of computation says that elims are post-inverse to intros. So that's kind of the most basic thing that you might ask for out of a logic, is that when I do introduction followed by elimination, then I can reduce by pulling out what I put in. Okay? And this is kind of a way to give an intrinsically constructive justification, because what we're doing here is saying that a proof is a program, and I can always reduce it. And this is where functional programming comes from, too. Okay? So like, if we do a props as types thing and annotate this with proof terms, so M1 there, M2 there, the pair M1, M2 there. Yeah, thank you. Take away true. Okay. If we say M on top, first of M on bottom, M on top, second of M on bottom. Then if we annotate our derivation here, M1, M2, the pair M1, M2, then this would be first of the pair M1, M2 down there. Then we're saying that, well, now we've named that M1. So what we've given is a beta reduction step that says first of the pair M1, M2 steps to M1. OK? So the methodology is, at least if you start from natural deduction, you divide your inference rules up into intros and elims. And computation arises by saying, whenever I have an elim, that's supposed to be post-inverse to the intro. So if I do an elim after an intro, I pull out what I put in. And you can view this as a check on the logic by saying that, well, if I think of, one way to think about it is I think of the introduction rules as defining the connective. I think of justifying the elimination rules by this process of computation, which is checking that the elimination rules don't take out more than the intro rules put in. Okay? So this is kind of why, as a type theorist, we kind of prefer to have type systems where things are divided up into intro and elim in this nice way, and then you just check that things fit together. And that's a good sanity check that overall the language is going to make sense. Okay? Any questions about that little detour? So one thing that screws up that kind of picture is axioms, in particular the univalence axiom. Okay? So one property that you'd ask for about a programming language is what's called canonicity. And canonicity is just one way to formalize that I can always run a program. It's kind of the weakest possible way to insist that I can always run a program. So what you ask is, if you have a closed program of some ground type, like nat, for example, then there exists a numeral k, let's say, such that m runs in some number of steps to k. Okay? So all this is saying is that if you have a closed program of a ground type, so we're not asking anything about function types or anything like that, we're just saying if you write down a program that's of type nat, then I can run it and figure out like what numeral that program actually meant. Yeah?
Is there a formal definition of ground type?
No, I mean like nat, bool, like it's kind of.
That's it, right?
Sure. I mean like, yeah.
A type that is expressed by a zero place constant.
A type that is expressed. OK. So like.
Has no argument.
Like the type itself has no arguments is how you, yeah. Yeah, I'm not sure.
What is the variable?
Right. Yeah, I mean, what I mean here is basically just base type probably inductively defined so that like I at least want like two alternatives. So like you could reduce it to bool, right, which would be the most basic one, which is saying if I write down a program, then I can run it and get a bit out of it. You just want to be able to see something observable. And yeah, I don't think there's a definition that captures the class of things that I'm talking about here. Yeah?
So maybe it's possible to generalize this property into introducing notion of canonical form.
Yeah, yeah.
So for example, if you have a term, closed term of type A and B,
Right.
you should reduce to
Yes.
something in introduction form, and maybe there you do not have to mention the notion.
Right, that's true. Yeah, so sometimes what people will do is kind of generalize this. So you talk about what the values are for each type. But the nice thing about canonicity, as stated here, is that it gives you a lot of freedom with what you do with all of the other types. Right? So it might be that when I write down a closed program of type pair, I don't run it. Right? I just say that any program of type pair is good. And then I kind of push the computation to when I'm actually doing the projections of the pair. Okay, so like you can play with evaluation order, right, and think about different operational models. Canonicity is just saying, I don't get stuck when I write down a closed program of type nat. So I think this is kind of important for the higher dimensional perspective because, for example, I have pretty much no idea what in general you're supposed to say about when that's an identity type, right? So like, I don't want to, in my theorem statement, insist that you say something in particular, because I don't know what the values of like id on the sphere are supposed to be. So the nice thing about canonicity is that it doesn't force you to answer that question immediately in the theorem statement. You can sort of play with it in the proof and figure out what you're supposed to do. But it's at least saying that when you write down a closed program of type nat, then you can run it. So you can think of this as like the interface to your programming language from the outside world. Somebody's going to write down a closed program and say, give me the natural number that I tried to compute.
So we're trying to compute something else like on a list of natural
Yeah.
numbers or whatever. Then
Yeah.
presumably, I guess, does one say, oh, the same argument would work in that case, or is there some meta theorem that says?
Or, well, you can always write the program that gets the first element of the list and run that one. And then run the program that gets the second element of the list and run that one, right? So like you can kind of reduce, so there's something called contextual equivalence, and this comes up there too, and you can kind of reduce a lot of things to bool or nat by sort of just writing the appropriate thing.
There's also the related property of eta.
Yeah.
The eta expansion property.
Okay. How is that related to canonicity?
Canonical forms property and open functions.
Yeah, right.
So if you try to state canonicity by saying if you have a type, if you have a term of type, a closed term of type unit,
Yeah.
then whenever you have a finite evaluation of
Yeah. I mean, we don't have non-termination, so unit's
yeah, so
not such a good one to pick.
No, but with unit, I would like to say, I would like to even weaken this bullet
Yeah.
by saying something like, then if it doesn't run forever, it has
Yeah.
to end in unit. In
Yeah.
TP.
Yeah.
Would that be the same thing as this?
Like, would those two theorems be interprovable? I don't know in the absence. I mean, because we know that all programs terminate, so it's not really giving you
Oh, in this sense
two
that they
things.
will all
Well,
terminate.
I mean, sorry. If we prove canonicity, like intended meta theorem is that all programs terminate. So like in the language, once you've proved that, you don't have two options there.
That's getting stuck on an axiom how it's termination.
I don't know. Like, yeah, I mean, so like it could, like a good statement of you don't get stuck would be, if I have something of type unit, then I can run it down to the empty tuple. Modulo the fact that maybe you have some kind of eta rule that gets you there in a shortcutty sort of way that like, so like when your type is in HProp and you don't have any computational content there, like you might do something silly along the way that only works for unit but doesn't work for nat or bool, right? So like if you say it's bool, then there are some programs you can write down where you're supposed to get true out, there are some where you're supposed to get false out, and you can tell the difference between the two. Okay. Yeah.
What is exactly the reduction relation?
We don't know yet. I mean, that's kind of up for grabs in your language design. But so far, it's going to include beta steps like this. Yeah. I mean, like, I'm not talking about a specific programming language yet. I'm just talking about that as a guide on designing programming languages. OK. Well, that was sheet number 1. OK. So everybody know how you can get stuck and violate canonicity with univalence? Or should we go through that? Go through it? OK. So if we take intentional type theory plus the univalence axiom as an axiom, so we state, how do people write weak equivalence these days?
The same as you.
What?
Whatever you do.
OK. Weak, right? So univalence axiom says just EQ? OK. EQ id at U A B eq A B. Do anyone want me to unpack that, or are we good with that statement of the univalence axiom? OK. Yeah, I mean, so given by the function, yeah, like that'll come up later, but yes, like formally it's the map that does the J on the identity and then gives you back the identity function there. But yeah, OK. So point being, OK, we've got the univalence axiom. Let's call this univalence. Now we would like to write down a closed term of type nat that doesn't run to a numeral. OK? Yeah. Well, so that's, I mean, yes. So like, you can say that you're not playing the game, but usually I don't think of axioms as assumptions because I'm never going to discharge it, right? Yeah, I mean, I would like to be able to run programs that use univalence, and I don't usually run open code, so yeah. Yeah.
Which direction are you going to use it for computation?
I mean, I haven't said how I'm going to use it at all yet. I'm just saying this is the univalence axiom, and now let's write down a stuck term, okay? Okay, so if I pick a type family like monoid, so how do you define monoid? So monoid on x colon u would be sigma binary operation x arrow x, sigma unit x, sigma associator, et cetera, right? So like I did this one before. Everybody good on that? Yeah, okay. So like it doesn't even matter that this is monoid. It's just like we need a particular type family. Okay. So if I have a particular type family, then the other ingredient I need is transport, right? So if I have x colon a proves b is a type, if I have alpha, which is m1, id m1, m2 in A, and I have, well, let me just curry it so that it's transport x colon a dot b with alpha will go from b of m1 to b of m2. Good? Okay. So now using these, we can write down a stuck term of type bool by saying that, well, okay. So if we take bool, we can write down a weak equivalence between bool, and I'm going to drop the W. We can write down an eq between bool and bool that's given by negation, right? So define this to be, I don't know, like not as an isomorphism is the negation function, and then some proofs of some things, right? Okay, so everybody believe that not is a weak equivalence between bool and bool? Okay, so then, now that we've got that, if I make a monoid on bool, let's call that, I don't know, M is a monoid structure on bool. So what's that going to be? That could be like and true, and then some proofs. Okay? So if I do transport at monoid with not, so in general, what transport at monoid, let's say that I just like look at this bit of it. What's transport at monoid? Transport at monoid now is saying that if I have a path in the universe between A and B, then if I have a monoid on A, then I get a monoid on B, right? So transport is giving us this generic programming or code reuse or something like that, which is saying, well, I've defined my monoid structure on A. I know that A is isomorphic or equivalent to B. Derive for me, please, the monoid structure on B that results from transporting the monoid structure from A along this isomorphism. Okay? So in particular, if I pick not here, that's going to be a path between bool and bool. And now I've got a monoid on bool. That's that. That's my M over there. Therefore, the whole thing is a monoid on bool. Okay?
Well, this term doesn't have univalence. I mean, you want univalence.
Oh, yeah, sorry. So if not is my equivalence, then what I need is let me call it UA applied to not as an isomorphism, where UA is that direction of the univalence axiom, right? The interesting one, right? So UA is the thing that says that if I have W, which is a equivalence between A and B, then I now have a path in the universe between A and B.
Interesting troubles.
Yeah. Yeah, I mean, like, this is like the troublesome one, right? Okay, so now what I've done is write a monoid on B, and then, like, if you want to actually get it down to type bool, then take like the dot U projection from that, which will actually be a Boolean, right? Because a monoid has the binary operation and the unit. Okay. Okay. So now I've written down a closed program of type bool, right? So canonicity for bool, if I did it like this, then it would say that instead of there exists a numeral k, it would just say that either it runs to true or it runs to false. Okay. But this term doesn't run. And the reason is that in intentional type theory off the shelf, the only reduction rule that we have for transport, so transport's derived from the J elimination rule for the identity type. And if you write it out using J, then you see that the only reduction rule that we have is that transport on reflexivity is the identity. Okay? But the whole game is that we wrote down a non-reflexivity path right there using the univalence axiom. So transport runs into this axiom and then gets stuck. Okay?
This argument is assuming consistency of the type theory.
Well, it's just a statement about, I mean, yes, like I haven't proved that there is no reduction for you. I'm just like informally arguing that there is, but I think it like should just be by inversion on the operational semantics that you can see that that's true. Like, yeah.
I don't understand. I mean, you just said if
Yeah.
UA is an axiom, this term is
Right. I mean, like, to formally prove that this doesn't take a step, we'd have to consider all of the operational semantics rules. But I think just by inversion, you see that there's none that apply to a term of this form. So I don't think you need consistency.
Two troubles that you have brought in.
Yeah.
I don't say which they are. But
Okay.
so this is a mess because there are some ingredients here that don't work.
Okay. Yeah. Okay. So, right. I mean, yeah.
Go through this monoid business.
No, I mean, there's probably a simpler one. Like, I like bringing up the monoid one because it's a nice example of code reuse, and like, it's kind of my like standard first factorial kind of example of this stuff. But yeah, I mean, we could have done it more directly, right? Like, we could have just taken. I mean, if you want a more direct one, do transport at x dot x with univalence axiom applied to not on true. Will be another point of bool that's not, yeah. I mean, it's kind of a silly one because you're just saying, please apply the negation function to true in a roundabout way. But yeah, okay. Like using the monoid kind of example, you can kind of see why this might come up in actual programming. But yeah, okay, yeah.
And you can take the identity function.
You can take the identity function, sorry, from.
Bool to bool.
It doesn't have to be
Yeah.
negation.
Yeah. I mean, if you have univalence axiom on the identity equivalence from bool to bool, then at least propositionally you know that this is equal to reflexivity. It doesn't reduce to reflexivity, but at least propositionally you know that it's equal to reflexivity. And so there it's kind of clear that like you're kind of close to the computation rule that already exists. But when it's negation, then like you're nowhere near it because you're writing down this thing that is manifestly not the identity function.
But don't you know that if you have
Yeah, that's the next thing I'm going to do. Yeah, exactly. Okay, so like the next thing I want to do is to suggest that when you, okay, so like what I wanted to say there is if you just kind of toss in an axiom, then you can no longer compute with the rules of reduction that you already had around. So essentially we just like gummed things up by tossing in this axiom, right? Okay, so we obviously want to get out of this mess. So how can we get out of this mess? Well, one point that I want to make is that if you kind of unpack what the axiom is, what the Univalence axiom is, you can see it in a way that looks more like introduction and elimination rules and less like just an axiom. So if you, let's see. Let me do it up there because I've already got half of it. So if you unpack what's going on with the axiom, then from the univalence axiom, you get, well, first of all, this, right? So I get that an equivalence determines an identity. I also get, and we were using this before, that transport at x dot x with alpha, where alpha is a path in the universe between A and B, determines a function from A to B. Okay? So if you want, you can kind of, I'm going to argue, think of this as an intro rule and this as an elim rule. Okay? If I transport backwards, so if I do transport x dot x, is the x dot x notation making sense to everyone here?
I'm confused by that.
Okay.
Are those both the same case?
So it's the same case of transport. Sorry. So x colon, I realized that I was slipping into notation that I used. So here I'm writing the family for transport. Where'd the rule for transport go? I'm just subscripting with the family for transport. And one particular interesting case there is x colon u dot x. Right? Is that okay?
That's
The family.
Identity family
Yeah.
on the universe.
Identity family on the universe. Is that okay as an argument to transport? Yeah. Yeah, I mean, so like I think of transport as being a primitive term former that has a binder there rather than a lambda. But yeah, if you want to parse it as a function, then you have to put in a lambda. Okay? Okay, but so if I transport with the same family on alpha inverse, well, we know that that's going to go back from B to A. Good? Okay. And I know generically that transporting by alpha composed with transporting by alpha inverse is going to be homotopic to the identity, and et cetera, right, in the other direction. So I can reconstruct the weak equivalence between let's see, I can go from eq to id that way, and then using transport, I can go back, right? I'm now reconstructing my equivalence between A and B by saying I've got transport alpha on one side, transport alpha inverse on the other, and then proofs that it composes to the identity. Okay? So if you want to think about it that way, you've sort of got intro rule here, elim rule here, and from univalence, you also know that when I put the elim after the intro, that is when I get myself into a situation like transport x dot x on ua of fg dot 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 for the rest of my equivalence, then in fact, I know that this is at least identical to f. Okay? So from univalence, you can conclude that when I do a transport on explicitly constructing a weak equivalence, saying that that's a path, then using transport to pull it back out, I get out what I put in. Elims are post-inverse to introduction. Okay?
I didn't understand to the left, the capital A capital.
Oh, I was just saying that, like, from the generic rules for the identity type, we can reconstruct an equivalence between A and B from A to AB. Right? So using,
The other half of the univalence.
yeah, I mean, I can do it in one shot by using J, right? That's sort of the canonical map that the univalence axiom asks to be an equivalence. But I think it's a little bit more instructive, at least in terms of the computational interpretation, to think of it as, well, it's the map consisting of transport this way, transport that way, and then some proofs that you derive. Okay? And you can even prove an eta principle that says that any path in the universe is UA applied to, and then you kind of expand into these transports. Yeah?
Could you give a more general example?
Well, so I already have that, right? I mean, I already have like transported a general family as part of my type theory. But I want to,
You view it as defining it
well, okay, yeah. So like, right, I'll get there. The thing I want to say is that I kind of do think of transport as at x dot x in particular as the lim for this, because that's exactly the name in the syntax for please pull out this component of, like, that's the projection from the path, right? So if I think of this, the univalence axiom is saying that id at u is equivalent to ekb, then this is pulling out the bits of that, right? That's like projection. Okay, so that one I think has special status. But yeah, like I'll get there in a second. But the main thing I wanted to say is that, like, okay, so now this presentation kind of makes it look less like an axiom and more like intro and elim rules, because I can go from eq to id, I can pull stuff out of id, and it all fits together with beta reductions, right? So this is kind of a beta rule. But what in the world justifies giving intro and elim rules for id u? Okay, that's the weird thing about the univalence axiom, is you're taking a type that in some sense already exists, the identity type, and adding intro and elim rules for id at u that are different than the intro and elim rules that are already generically there for the identity type. Okay, so that's the weird move here that we're making, is we're sort of giving intro and elim rules for id at u.
But you could say you're giving a new intro rule for identity, except that EQ itself already involves the identity. So
Yeah, that's true. Yeah.
that's what makes it sort of nothing.
Yeah, and you could also say that you give a new interlude for id here, which shows with maximum clarity that you have changed the interpretation of it.
Right.
So it isn't id any longer.
Yeah.
It's another equivalent.
Right. Yeah. I mean, so, okay. So, like, I mean, everybody here already knows the answer to, like, what in the world justifies this. But, like, the reason I asked the question that way is because, like, if you're talking to someone who kind of comes at it from the type theoretic perspective, then it's really weird. And this is something that, like, I had to get over and Bob and I had to get over when we first saw this stuff a few years ago. It's like, this is a really weird move, okay? But what the move is saying is that, of course, we're interpreting types as setoids or groupoids or weak infinity groupoids or what have you. And so every type is coming with a notion of path in that space or morphisms in the setoid or morphisms in the groupoid or whatever. And we're just defining that for this particular case, right? So we're not taking the standard interpretation of the identity type as the least type containing reflexivity, which is what justifies the Reffel and J rule in sort of standard intentional type theory. Instead, we're moving to this higher dimensional world. But
I mean, one might say that, I mean, 'cause you still have the J rule.
yeah.
And so
But, like,
that sense,
in my
the
view,
identity of U is still the least type containing reflexivity.
yeah.
No,
Yes,
but
it is,
it's
but the
equally
universe
different.
changed, right?
Yeah.
It's still the least one in a different world.
Right.
Yeah.
But he was saying that it wasn't the least.
Yes.
Well, okay, yeah. If you're in, like, sets, It's not.
You change.
Yeah, I know. I agree. Yeah, like either we changed the meaning of the type or we moved the world and kept the same definition, but then that definition means something different, right?
It's the same thing.
Well,
in
okay.
different
Yeah, okay.
semantics.
Right.
It cannot mean the same. It's the same thing that means different. It's the same expressions that mean different things in different semantics.
Okay. So like, good. So morally, right, everybody sees like the way that we get out of this mess is that we want to think about intro and elim rules for id or path at each type, and then that's all going to fit together into kind of a groupoidal picture of some sort, right? So that's like the move you make that gets you out of this seeming like blah from a type theory perspective is just like, we're thinking about groupoids, okay? Okay, so what I want to talk about next is two-dimensional type theory, which is a particular formal system that makes all of this kind of work out technically. And it's kind of the simplest possible step above extensional in the sense of equality reflection in UIP kind of type theory, in which we can get at these issues of computing with groupoids, right? So Bob and I wanted to carve off the simplest thing that we could actually get our hands on. And it's nice because in 2 dimensions, we kind of know what groupoids are, and in higher dimensions, like the definitions get a lot more complicated. So it's a useful special case to look at. Any questions about this before I kill it? Okay. So for 2 dimensions, two-dimensional type theory, we're going to have a couple of forms of judgment. Sorry. We're going to have a judgment that, well, okay, so if we start with non-dependent types, then A as a type is really going to mean that A is a groupoid. M colon A is really going to mean that M is an object of A. So those are your normal judgments of type theory. Instead of just having the identity type, we're going to give a judgmental thing. We're going to give a judgment that underlies the identity type, if you will. So we're going to have a separate form of judgment that I write like that. M is equivalent to N at A, which is going to mean that M is a morphism of A. Yeah, okay. Alpha, thank you, good catch, is a morphism of A. Okay, and already you can see why we stopped at 2 dimensions, because if we didn't, then we'd need beta is a thing between alpha and 1 and alpha 2, and et cetera, right? So in this style of presentation, you're kind of explicitly putting the level into the syntax. So you can see that everything is of H level 3. Did I get the indexing right? Yeah. So like everything here is going to be of H level 3. That is, everything's going to be strictly a groupoid. And the way that you can tell that is just like there's no syntax in the type theory for paths between paths. Okay? All right. So this makes our lives easier. But we still, yeah.
Does your type theory still have the id as a type property?
Yes. Yes, we do. So id is going to internalize this judgment in a rather nice way. So you just give rules saying that if I write down an alpha, then in of alpha is in the identity type, and conversely, if I have something in the identity type, then out of alpha, out of M goes back to there. So that'll come later.
So is there something around here that has dimension 2?
Yeah, so we'll add particular base types that have dimension 2.
And so we'll see the geometric.
Yeah, so like we can add, for example, among the A's. So like the nice examples are we can have set, which is going to be a universe of H sets up to ISO. Okay. Or in 2-dimensional type theory, we can do the circle at least in the interval and higher inductives that don't have anything higher than dimension 2.
The
well, dimensions, okay, yeah. So like,
Well, I think it's two-dimensional.
is the type theory as a whole. Yeah. So like the type theory as a whole is a 2-category. Individual types are groupoids. So like, yes, the terminology gets a little skewed.
You mean it's the 2 and 2 category?
Yeah. So like my type theory as a whole has objects, arrows, and arrows between arrows. Each individual type has objects and arrows. So the 2 comes from that, which is.
I didn't get that. You pointed at an object and said arrow.
Well, so like if I think of the type theory as a whole, then I have A as a type, right? I mean, just looking at the judgment structure of the type theory, I have A as a type. I have X colon A proves M colon B, which I can think of as a morphism between A and B. Okay. And then I have alpha, which relates M to N, which I can think of as a 2-cell between those morphisms. Okay. So the type theory as a whole has 2 dimensions. Each type in it is 1-dimensional. Okay. Which is where the name comes from. Also, calling it 1-dimensional type theory probably wouldn't have got it accepted to a conference. So like, you know, start the indexing in the right place.
1-dimensional type theory should be simply type theory.
Yeah, like regular set theory kind of type theory. Yeah. Okay. Good. So, but the main thing is, well, okay, so we're going to have gamma is a context, so that's also going to be interpreted as a groupoid. And then, of course, we have open types and terms. So we'll have gamma proves that A is a type, and gamma proves that M colon A. And you've seen enough of like categories with families and C structures and stuff like that to know how these get interpreted. But basically, this is A is a functor from gamma into the category of groupoids. And then this is a section of a projection, or however you want to formalize open terms. Okay?
These things you keep writing in brackets are aspects of a model you can use as for checking consistency?
Yeah, I mean, these are like aspects of the groupoid interpretation of type theory. So in a sense, what we're doing is taking the Hoffman and Streicher groupoid interpretation and reading it back into syntax. So we're making a syntax that more faithfully models the groupoid interpretation, and we're adding a bunch of stuff in that's true in the groupoid model, but not in general. Okay? But I think it's more just like, this is what you want to have in mind when you're thinking about this syntax. Okay? All right, so for example, from this interpretation, you get a bunch of structural rules or sort of judgmental principles that are just sort of always present in the type theory. So the reason that you expect transport to exist, so transport's conveniently already on the board, except I'm going to make a little move here and say that I want alpha to be M1 is M2 in A as a judgmental thing, not as the identity type. But the reason that I expect transport to exist is exactly from thinking of an open type as a functor into groupoids, right? So what does that mean? That means whenever, so if X colon A proves B as a type, whenever I substitute something in for X, M1 for X there, M2 for X there, well, I expect that that's going to be a type and that's going to be a type because a functor into groupoids delivers you a groupoid every time you plug in an object, but also it has an action on morphism. So whenever I have a path in A, that determines a functor between the corresponding types, which is exactly what transport is. Okay? That make sense? Right, so basically this interpretation of I'm talking about groupoids suggests certain things that we put into the syntax as generic programs, which is a word that gets used in programming languages for sort of programs that exist independently or sort of exist for a collection of types, right? Every type, in particular every type family X colon A dot B, is going to have this kind of transport. Okay, so like what else do we put in? Well, because we're talking about groupoids, we know that we're going to have ruffle M, which is going to say that M is M, that we're going to have alpha inverse, which says that N is M, if we have alpha, which says that M is N, and we're going to have alpha 2 compose alpha 1, which says what composition says, etc. Okay, so because we're talking about groupoids, we put in reflexivity, symmetry, composition, etc.
Can I just say something?
Yeah.
The rule,
Yeah.
one is of course you need to say why is the rule valid? And
Right.
It is valid now because you charge the topmost judgment
Yes,
with
exactly.
precisely the meaning.
Yes, exactly. Right, so like it all comes back to this thing in brackets here, right? Which is why I wanted to say that sort of right away, which is that when you say you're a family of types, you're saying you're a functor. You're not just saying you're a type for each object that you plug in, okay? And in fact, that's going to come out in the computational interpretation. Okay, the other thing that is like a good one to mention, because we'll need to talk about it later, is that we don't just have transport. So transport is sort of functoriality of open types. We also have functoriality of open terms, which is what's called map or map on paths in the hot repository, which is the idea that if x colon A proves m colon B, and alpha says that m1 is m2 in A, then I get something which I'll probably often write as m with alpha for x. If that gets confusing, I can switch notation, but it actually kind of works out nicely to say that that's the thing that relates m under m1 to m under m2. Good? Yeah, okay, so if B is actually dependent on A, then I need to pick here B of m2, and then that's not in the right fiber, so I insert transport at x colon A dot B with alpha. Okay, but if it's not dependent, then what I wrote before works, right? Okay?
So is the dependent and the not, do you assert both the dependent and the non-dependent version, or do you?
I just assert the dependent version, okay? And the reason I can get away with that really easily is that the other thing I should mention is that two-dimensional type theory is a type theory of strict groupoids. So in addition to like path judgment, there's also a rather extensional notion of equality, which I usually write like that. But so, for example, you can say that A is equal to B, M is equal to N, okay? And it's a rather extensional notion in the sense that we'll add equations for a bunch of things that are true in the model, like alpha 1 compose alpha 2 compose alpha 3 will be triple equal to alpha 1 compose alpha 2 compose alpha 3. So we'll know associativity and inverses cancel and reflexivity cancels and blah, 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 up to this notion of equality. So that's all silent in the proof term, okay?
Expressed category theoretically, it's strict equality, the three bars.
Yes.
And can it be understood as definition of equality?
I don't know. Yeah, I don't know. I mean, it would be, I don't know how to make that come true, make enough of these come true definitionally. I haven't tried yet. Like, I don't really have a guess either way. Okay.
So the transport will become an identity then?
Yeah, so like in particular, not only do we say that each groupoid here is strict in the sense that these operations have associativity in unit strictly, all of our types are going to be strict functors. Okay, so I'm going to have that transport x colon A dot B is going to on alpha 2 compose alpha 1 is going to be equal to transport with alpha 2 compose transport with alpha 1, okay, etc.
But should I also take into account the B?
Yep. That's like the key thing that I'm about to get to. Okay, I just wanted to set up like the framework we're working in is a lot of these things are equations. So we have like the interchange law relating this gadget and the composition, and basically all of the stuff that holds in a 2 category are just there as equations. So these are all things that you can prove in intentional type theory using the identity type. We just take them as equations.
So this also means you can substitute as real once you have one of these equations?
Yep. Yeah, it's a congruence. It's just like replace equals for equals. So it's like we're codifying the groupoid interpretation as done in sets or extensional type theory or something like that. Okay? So in particular, we charged each type family with knowing how to transport. Okay? So the key to the computational interpretation, right, is, so there's these sort of generic structural gadgets like associativity and stuff. But what do you need to know for each type? Okay? So when you define a type, what do? Well, you're defining a groupoid, but you can kind of codify what this looks like in the type theory. And then in the time that's left, we can go through a couple of examples. So to define a type A, you have to give 1, a formation rule for the type A itself, 2, intro and a lim for terms of type A, 3, intro and a lim for paths in A. So this is kind of like saying, what are the objects? You know, here's a groupoid. What are the objects? What are the morphisms? And then you have to give a bunch of equations for these generic judgmental gadgets. So that will include, when I define a formation rule for A, I also need to say what happens when I transport at A. Let's call that A1. Okay? So when I'm defining a family A, I need to give its functorial action as a functor into groupoids. So I'm going to give a rule that says, well, if I'm transporting and the family in question is A, then what do I do? Okay? So that's kind of viewing transport as a generic program that's guided by the structure of the type family.
So you keep saying that we're
Yeah.
familiar with
Okay, sorry.
phrase.
Type family is just open type, right? So like gamma proves A is a type. Call this a type family. Basically, family gets used for anything in a context. Okay? So an open type, or a family of types indexed by the context. Any other terminology thing that I'm slipping into? Yeah.
Since you began with Jensen,
Yeah.
maybe take away a lim on that blackboard and just say that to define the type A, you don't need a lim to define it.
Well, okay. To present, maybe? Yeah. Like, I'm not totally willing to call this a definition in that sense yet. Like, what I was trying to say is to give rules for a type, syntactic rules for a type. Here's what I do. But, yeah, I mean,
Are you formulating a rule of a formal type theory?
here?
You say to present.
Yeah. Yes.
This is one of the rules.
Well, so here I'm like trying to spec out the thing that I'm going to do several times when I tell you what pies are and what the universe is and stuff like that, just so you have a template for it. Okay? So like, I think I agree that we could phrase it as, to define a type, you could phrase it like this. Okay. But then for, I want to give lim rules for m:(A) justified by beta. Okay, so I want to give computation rules and stuff like that. Also for paths, I want to give a lim for paths in A, also justified by beta. Okay, but in fact, I'm going to get kind of extensional about it and also add in some eta rules and rules saying how these things interact with the various judgmental gadgets. So when I define an open term, just like when I define an open type, I say what transport does. Whenever I give you a term, I say how it's functorial by defining what m under alpha is. Okay? Whenever I define a type, I say what reflexivity and composition and inverses are for that type in terms of the canonical paths in that type. So I'm spelling out, how I do the groupoid structure. Okay, so like that spec, like let's just hold on to that for a second and do some particular type family. Any ideas? Arrow? Okay.
So since you're stopping at dimension 2, you could do the following. So we would take your alphas could be paths.
Mm-hmm.
Paths in space. Not forced to that by homotopy. There's nothing that forces you to do that.
No. I mean, why would I get associativity of composition? And yeah.
More paths. Use more paths so that the associativity comes out right. But the problem is inverses, actually.
Yeah. I mean, okay. If there's some model where you can get everything to hold strictly, then yes. Okay. All right. So let's play this through for arrow. So basically, I want to tick off. Let's do A arrow B. Then we can do the universe to explain univalence. And if there's time, we can do the circle to sort of see how the higher inductives play out. Okay. So good. We've got half an hour. Okay. So yeah. Yeah. I mean, I've played with different versions of it. Like in the paper, there's like pi. There's sigma. At least in a tech report somewhere, there's like U, which is really set. There's elements of a set. You want bool so that you have canonicity. Like I've mostly written out the circle, but haven't like written that up anywhere. But yeah, you can kind of get it to play out for all the basic stuff. Also, I should mention, then you can do the identity type, which we're not taking as baked in, right? So you can give rules for the identity type and see that you get reflexivity in J. Okay, that's a little bit interesting to see how you get J, but yeah.
So just as an idea,
Yeah.
you could have the arrow groupoid,
Mm-hmm.
you could have the interval groupoid, and then the identity should fall out, right?
Yeah, you could do that. Yes, and I think you could actually do that in this kind of setting because you have the judgmental notion of paths. Yeah. Yeah, okay, but let's do arrow. So my formation rule says that gamma proves A arrow B is a type if gamma proves A is a type and gamma proves B is a type. Okay. Kind of a boring rule in general, right? Like, I'm just saying these things are types. But remember that when I say this kind of thing, the onus is on me to explain how transport works already, okay? So I want to know how transport works at arrow. In fact, well, I need to say what the objects are before I can actually say that. So I'm going to have lambda x. I'm not going to write out the rules. I'm just going to have lambda and application as my terms of arrow type. Okay. And now we want to explain how transport works. Okay. So if I've got x colon a naught dot a of x arrow b of x, that's a family of types, right, over a naught. So I can say, ask the question, what happens when I transport at that with some alpha which says m naught is n naught in a naught. Okay, and then I'm going to get some f, which is a of m naught arrow a of b of m naught, and I'm going to want to come up with, if I remember my rule for transport, a of n naught arrow b of n naught. Okay, yeah.
So what,
Did I screw it up?
What's the connection between A naught and gamma?
So I am trying to, for the talk, restrict myself to one variable in the context. So let's just take gamma to be that. If you want to have, so actually, in the formalism, there's a move where I have like n-ary substitution and n-ary paths between substitutions, but I'm trying to suppress that just for the talk. So let's just assume we've got one free variable. Okay. Okay, so let's see. I guess since more people are category theorists than I am, like maybe a picture. So how do we draw this? I start off with A of M naught, arrow B of M naught. What? Yeah, basically. Okay. I don't know. Like I always like do these things by type checking, and then like Steve is like, wait, I don't understand, and then like you have to draw the thing two-dimensionally, and then it's fine. Okay. So like on top we start off with F, which is that, because that's the thing we're transporting. Down on the bottom, we want to go from A of n naught to B of n naught, because that's the type we're trying to inhabit after the transport. Everybody good with that? Goal to show there. Okay. So how do I do it? Well, I've written it like a square for a reason, right? To go back up here, I have transport at x colon a naught dot a of x with alpha inverse, right? Because alpha inverse relates n naught to m naught, and A is a family, right? I already told you that A was a family of types. I already told you that B was a family of types. Therefore, you know how to transport at them. Apply that going up, come back down using transport at B with alpha, and then you're good. Okay? So we define the transport overall to be this composition. Okay? Which is to say, do you want me to write out the proof term? Lambda y dot transport at B with alpha applied to transport at, applied to F applied to transport at A alpha inverse applied to Y. Okay? Give me an argument. I'll send it back using alpha inverse. I'll hit it with F, and then I'll send it forwards. Okay?
Except that this doesn't come in the right order, but it doesn't matter.
Yeah.
Because you have to give the introduction rules before you can do this.
Right. Yeah. In fact, here I used the elimination rule as well. Yeah. Right. Yeah. Yes. Okay? Okay. So that's how transport works. And what this is illustrating is the general pattern that transport is driven by exactly this type family. So the way that I get out of trouble when before transport only computed on reflexivity and otherwise was stuck is that the new idea, which just falls out of the groupoid interpretation, right? This isn't like my idea. This idea's been around for a while. Like, drive transport by the structure of the type family, because each type family comes with its functorial action. Okay?
I don't think you need the groupoid interpretation for that.
It comes up in setoids too, yeah.
Well, I mean, it is true in the type theory.
Yeah, I mean, so like, yes, good. So like another good point is that this is already an identity that you can prove in intentional type theory. Okay, but I'm going to take it, at least for my purposes for today, as a triple equals. So I'm going to say that these beta steps for transport hold as equations. And we can ask whether that's the right thing to do in general. Okay, so now I've given...
You're not introducing any new paths at this point.
Right, yeah. I've given a formation rule. I've given introduction and elimination. I've told you how transport works. Now I have to tell you what the paths are, right? So now we exploit the fact that we're doing groupoids to say that when I define a type, I get to say what the paths are. So for arrow, I'll of course say that if I want to give a path between F and G in A arrow B, then what do? Well, I use function extensionality and say that to do that, it suffices to give, for every x colon A, a path alpha between f of x and g of x. Okay, so my introduction rule for paths in arrow is function extensionality. My elimination rule is application, if you will, which says that let me just do the, oh, everything's non-dependent, okay. So, which says that if I know that f is g, and if I know that m is n, then app alpha beta is going to say that fm is g n. Okay?
Something forcing you to do this?
Forcing me to do what?
Have these rules.
Well, no.
No, there will be type theoretic considerations which say that this should be there. It should be there.
Well, okay, so like I could pick something less, I think.
Yeah.
Like I have the freedom to pick the groupoid, pick the morphisms in arrow to be something less than this, though I don't know what consequences that would have for like what you can prove, right? I mean, it would be like what you can prove in type theory without function extensionality. So I could just say like reflexivity here. No? Why? I mean,
we give a certain meaning to f isomorphic to g in B.
right, but we could give rules that were, I mean, as an axiomatic system, I think we could give rules that were sound but incomplete for that meaning. And I don't think anything would go wrong. But
When you get canonicity, when you try to prove canonicity.
yeah,
You wouldn't have lambda abstraction in the groupoid model.
right. Yes. I mean, it wouldn't. Okay. So maybe something would go wrong.
If I have a functor from A cross B to C,
Yeah.
then I don't get a map from, I don't
Yeah,
get a
yeah,
functor from
yeah,
A
yeah.
into
Okay, yeah.
the set.
So I think you might not be able to do the semantics in groupoids.
You wouldn't get the exponential laws.
Yeah. Right. Right. Yeah. Okay. But anyway, like you also have kind of a beta reduction that says that if I have a path application of a path lambda like that, then that's going to be beta with alpha for x, where I'm using this same kind of punning to have the two-sided version of this. So if I have an open path, that also gets kind of the substitution principle.
I think we also couldn't show that transport of the identity is the identity.
Okay. Yeah. That's totally plausible. Okay.
You also need an eta rule for this?
Yeah, so in fact, I put in, like, in the paper, there's, like, beta and eta rules for everything. And, of course, I should also tick off, like, how do I define reflexivity? How do I define composition? How do I define inverses, right? So, for example, I'd say that lambda x dot alpha inverse is lambda x dot alpha inverse. So that kind of commutes with that. So these are all equations that you can prove about function extensionality. Okay? All right, so does the basic methodology work here? Okay. All right, so I know people are starting to get hungry, but let's tick off at least the universe so that we can say that we did univalence. Okay? Okay, so to do the universe, let me just sketch it for you. You want to introduce a type set of H sets, a type L of S, where S colon set, which is going to be the elements of that H set. Okay? And then, because you get to say what's going on, you get to say that when do I have a path between S and T in
What's the
set?
difference? Oh, you mean if S colon set, then S can't be used as a type without
Right.
putting some sort of wrapper
Yes,
around it?
exactly. Yeah,
Couldn't we call set U so that we see that it's universe?
sure. Yeah, it's just going to happen that this is a universe of H sets because I'm dimension restricted. That's like the biggest dimension-y thing I can do, right? A universe of H sets is itself a groupoid, but if I wanted a universe of something else, then it would be a higher groupoid, and so I can't do that here. Okay? All right, so now I get to stipulate, according to my methodology, when do I have a path in set? And now I get to say, essentially, the univalence axiom as presented earlier in the talk, which is here I'm going to have what I was calling UA, if you will, of FG alpha beta, where F goes from A to B, thank you. S to T, G goes from T.
LS to LT?
Yes. Yeah, the problem with that silly coercion is I always forget to write it. L of S to L of T, G goes from L of T to L of S, and then alpha is a path between F dot G and the identity function, etc. for beta. Okay? So what I'm saying is I get to pick the paths. I've picked the paths to be isomorphism, so let me just call this iso because it's H set. Okay?
So what would happen if you replace the paths, the built-in paths with ID?
I don't have an identity type yet, so I can't make that move yet. Okay? But nothing once I have one.
Is it the case that we don't have to worry about triangle identities
Because it's H
below
sets.
dimensional?
Yeah. Yeah, because it's H sets, it's just an ISO. Yeah. Okay. And now, right, so like I've picked my paths. I have to define reflexivity to be the identity isomorphism, symmetry to flip the components, transitivity to do the thing that transitivity does, etc. Okay, so I'm just like ticking off all of my properties. But like one of them is I need to tick off what happens when I transport at x colon a naught dot set with alpha, and what happens when I transport at x colon u dot L of x with alpha.
U and set is the same thing, right?
Yes. Sorry. I got renamed. Okay, good. U. Okay. So what happens when I transport at x colon a naught dot u? Nothing? Okay. So people sometimes get confused about this one. Transport at when the family is constantly u. This is a path between m and n in a naught. Here I'm going to get s